Hi everyone, we have reached the fourth section, Advanced General Purpose Data Structures. In this section, we will take a look at some more interesting data structures that are commonly used. We will start with the concept of a priority queue. We will see some efficient implementations of a priority queue. In short, we will cover priority queue ADT, heap, binomial forest, and sort using a priority queue and heap. Now we move on to the first video of this section that deals with priority queue ADT and heap. In this video, we will perform basic operations on the heap using priority queue. Let's start with a priority queue ADT. A priority queue is like a queue in that you can enqueue and dequeue elements. However, the element that gets dequeued is the one with the minimum value of a feature, called its priority. We will use a comparator to compare elements and learn which one has the lowest priority. Here we have added some Java classes that will be used. We will use the interface named priority queue. Declare the methods for this interface. Check minimum. This method must return the next value to be dequeued without dequeuing it. If the queue is empty, it must return null. Dequeue minimum. This must dequeue the element with the minimum priority and return it. It should return null when the queue is empty. Enqueue. This should insert a new element in the priority queue. We would also like to do these operations as efficiently as possible. We will see two different ways to implement it. What is a heap? A heap is a balanced binary tree that follows just two constraints. The value in any node is less than the value in either of the children. This property is also called the heap property. The tree is as balanced as possible, in the sense that any level is completely filled before a single node is inserted in the next level. The figure shows a sample heap. It would not be really clear until we actually discuss how to insert elements and remove the least element. So let's jump into it. The first step of insertion is to insert the element in the next available position. The next available position is either another position in the same level or the first position in the next level. Of course, this applies when there is no vacant position in the existing level. The second step is to iteratively compare the element with its parent and keep switching until the element is bigger than the parent, thus restoring the constraints. The grey box represents the current node, and the yellow box represents the parent node, whose value is larger than the current node. First, the new element is inserted in the next available spot. It must be swapped until the constraint is satisfied. The parent is 6, which is bigger than 2, so it is swapped. If the parent is 3, which is also larger than 2, it is swapped. If the parent is 1, which is less than 2, we stop and the insertion is complete. Let's look at the removal of minimum elements. The constraint that the parent is always less than or equal to the children guarantees that the root is the element with the least value. This means the removal of the least element leads only to the removal of the top element. However, the empty space of the root must be filled, and elements can only be deleted from the last level to maintain the constraint too. To ensure this, the last element is first copied to the root and then removed. We must now iteratively move the new root element downward until the constraint 1 is satisfied. There is one question though. Since any parent can have two children, which one should we compare and swap with? The answer is simple. We need the parent to be less than both the children. This means we must compare and swap with the minimum value of the children. An ArrayBacked Heap is a fixed size heap implementation. We start with a partial implementation class. This class will implement priority queue, add the required Java packages, add the attributes, and implement the constructor. Given any index of the array, starting from 0, find the index of the parent element. It involves converting the index to 1-based form. So add 1, dividing by 2, and then converting it back to 0. So subtract 1. Find the index of the left child using this method. And find the index of the right child using this method. Swap the elements in the two indexes provided using this code. To implement the insertion, first implement a method that would trickle the value up until constraint 1 is satisfied. We compare the current node with the parent, and if the value of the parent is larger, then do a swap. We keep moving upwards recursively. Now we can implement the insertion. The new element is always added to the end of the current list. A check is done to ensure that when the heap is full, an appropriate exception is thrown. Similarly, for deletion, we first implement a trickle-down method that compares an element with its children and makes appropriate swaps until constraint 1 is restored. If the right child exists, the left child must also exist. This happens because of the balanced nature of a heap. In this case, we must compare only with a minimum of 2 children, and swap them if it is necessary. When the left child exists but the right child does not, we only need to compare it with one element. With the trickle-down method available, removing the minimum element is simple. If the number of elements is 0, we return null. Else, we first save the current root as the minimum element, then copy the last element to the root position. Then we decrement the number of elements, call the trickle-down method to restore constraint 1, and finally return the value. Now we only have to use it as an implementation of the priority queue. So we implement the relevant methods using our insert and remove min. So now we will override the check minimum method. This is our check minimum method. If the number of elements is 0, we return null, else we return the first element. Override the dq minimum method and the enqueue method. Next we implement the display text method to display the array in the proper format. Here it traverses till depth using for loop. If the parent is greater than or equal to number of elements, then it prints asterisk and returns. Here it prints the value of parent, and it calls the left child index method. Then it calls display text method recursively on the left child index, and it again calls display text method on the right child method. Now we will add the wrapper method for the display text method. Implement the main method. After this, implement the heap sort method. This sorts our array heap. The code is self-explanatory. Our main method and array heap class is ready. Let's save and click on Run. This is our tree. And here you can see we have traversed the array we stored. This is a huge array. This completes our array-based heap implementation. It has the same problem as our array-based queue implementation. That is, we need to know its maximum size beforehand. That's it for this video. We performed insertion and removal on a heap.